In Unit 6, we are going to look at properties of waves because light behaves as a wave, and we need to understand how waves behave, how they interfere with each other, and so forth. So first of all, simple harmonic motion is the source of waves. And just a reminder that simple harmonic motion is the vibration about an equilibrium point where a restoring force is proportional to the object's displacement from equilibrium. One example of this is a mass spring system. Now, there are mass spring systems. Oh my goodness, I had this all queued up. Here we go. There are mass spring systems like this one.
I'm filming.
At a playground. These are my children a few years ago on a mass spring system. And you can see how there's a restoring force. So they're tipping the toy back and forth, but the toy always wants to bring them back.
Okay, now I just need one person going. So put Rye on the motorcycle side.
Okay.
And that restoring force is proportional to the displacement.
Wait, just drive
Another
first.
example of a mass spring system that isn't necessarily what you would think is here's a backyard pool. Oops, let's see if I can get it. Here we go. Here's a backyard pool. The mass is the water, and the spring is the elastic pool around the water. And you can see that this dad has found the natural resonant frequency of this pool, and when he pumps at the right time, he increases the amplitude. So those are some sort of non-traditional examples. And now let's look at a more traditional example of a mass spring system. So this is in our O physics simulations, and we've seen a mass on a spring. And I'm going to skip ahead a little bit here. So if we displace the mass from equilibrium, we see what happens is the mass will oscillate back and forth around the equilibrium point. And the mass is always being pulled back or pushed back to that equilibrium point. Now, simple harmonic motion is also related to circular motion. Let's take a look at this. The horizontal component is the same as what we see on as the horizontal component of a oops. Let me run this again. And the time for one revolution is the period. That's also omega, the angular speed. So the angular speed times the time is that angle being swept out. Finally, we can graph this motion, and the graph is a cosine curve where the vertical axis is x. X is how far the object is displaced from equilibrium, and the horizontal axis is time. So in our notes, so now that we've looked at some examples of a mass spring system, let's look at properties of the wave that's produced. First of all, we've got amplitude. Now, amplitude is also the number before the cosine in the equation. And if I look at this graph here, I can see that this is 4. This would actually be x, the displacement from the horizontal. So if we're looking at a mass spring system where the object is oscillating left and right, where 0 is in the center, this object would be oscillating with a maximum amplitude of 4 to the right and negative 4 to the left. And typically we actually start here at 0 seconds. This horizontal axis is time. Okay. This number, this next number, let me highlight it. This 2 pi, that is our, that's our angular speed for this thing. And remember that angular speed is radians per second. On the then on this situation, 2 pi radians is one full oscillation. And we also know that angular speed is equal to 2 pi over the period. So the period here must be 1. And we can see that here, that the period for one full oscillation is 1 second. It's important to notice that time is what's on the x-axis here. And again, that this represents the position versus time graph. Okay, it's tempting to think that this value is the wavelength, but it's not. We have to look at the actual waveform for that, and we'll do that in a little bit. So here's another example. So just to practice a little bit here. Here we've got an amplitude of 3, and you can see the amplitude of 3. Here we've got an angular speed of 2, and the angular speed also equals 2 pi over the period. So if the angular speed is 2, then 2 pi over something equals 2, and it turns out that the period then must equal 2 pi over 2, or pi. And indeed, when we look at this graph, we see that the time for one full cycle is pi. This is 3.14. So that's just to sort of orient you in looking at these graphs. Let's see. Now, when we studied simple harmonic motion last year, we learned about how this oscillation back and forth is actually energy. It's at the maximum displacement. The type of energy is elastic potential energy. And in the middle, we have a maximum kinetic energy. So this is all about energy. And the bigger the, I should also say, the bigger the amplitude, the more energy that we have. So again, we've got amplitude. Period is the time for one complete cycle. Frequency is the number of cycles per unit of time. So period and frequency are reciprocals of each other. And then wavelength is the length of the actual wave. To figure out wavelength, we have to actually look at the waveform itself. So if this is meters, one wavelength is one complete cycle. And the symbol for wavelength is this Greek letter lambda. Oops, lambda. So when we are looking at waves as disturbances traveling through a medium like water or a string or a slinky, we can create a couple of different situations. One thing we can do is create a wave pulse. A wave pulse would be half a wavelength, or sometimes it's a full wavelength, traveling through the medium. So let's take a look here. Okay, so here I'll send a wave pulse. And there's the top view of it. And let's look at the side view of it. Now, what if we had the water continue to drip? Let's try that. So if we had the water continue to drip, we could create what is called a standing wave. So the wave just keeps going. We can create a standing wave with water. We can create one with a string. We can create one with sound. Now this wave, the pattern is moving, appears to be moving, so we would call this a traveling wave, but we can also create something called a standing wave. So here is a representation of a standing wave. A standing wave has two fixed ends and then vibrations in the middle. And the blue line represents a transverse standing wave, and the green lines represent a longitudinal standing wave. One common scenario that we see in physics questions is a tuning fork attached to a string with a mass on the end. And this is supposed to represent that. Now, that's really exaggerated. The amplitude here is really exaggerated, but the tuning fork is vibrating back and forth and creating this standing wave, which is a constant pattern. Okay, so we've seen how traveling waves can travel through the substance, and standing waves have the same, two waves have the same frequency, wavelength, and amplitude, and they're traveling in opposite directions. It creates a standing wave. Standing waves have some features to them. These points that appear not to move, these points that I'm marking in blue, those are called nodes. And then these points of maximum amplitude are called antinodes. Okay, so this was a lot of vocabulary in a short period of time. So let's go to a simulation, waves tutorial. Let's look at the waves tutorial. So a lot of these ideas are summarized here. So we have the definition of a wave, periodic disturbance that transfers energy, the medium, the material through which a wave travels. When we're talking about mechanical waves, they require a medium through which to travel. Tomorrow, or in the next section, we're going to talk about electromagnetic waves that do not require a physical medium in which to travel. Here's a picture of simple harmonic motion, which is the source of wave motion. And here's an example of a transverse wave and a longitudinal wave. We talked a little bit about period, frequency, amplitude, and wavelength. Here is a simulation of that. So we've got a longitudinal wave and a transverse wave. And we can see the wavelength labeled and the amplitude. The frequency would be the number of cycles per second. So we could take a stopwatch and measure to see how many cycles per second are being created here. Okay, so down at the bottom, I can see some important facts that we're going to talk about next. The speed of a wave depends on the medium through which it is traveling, not on its frequency or wavelength. The frequency of a wave is determined by the source. It does not depend on the medium through which the wave is traveling. And finally, the wavelength of a wave is determined by the speed and the frequency, and I have that formula there, but let's go back to our notes. Here's the formula for wave speed. Wave speed is equal to frequency times wavelength. If we break that down a little bit, wave speed is in meters per second, frequency is in cycles per second, and wavelength is meters per wave or meters per cycle. So you can see how the units work out to create meters per second equals meters per second because the cycles cancel. Again, the wave speed is constant in a given medium, and I'll just add, and it's determined, the wave speed is determined by that medium. And wave frequency is constant from one medium to another across a boundary. So I'll give you an example of this. The pitch of a sound is an indicator of its frequency. If somebody makes a noise in the other room of my house, the pitch of the sound doesn't change. So pitch is like this: high pitch, ooh, low pitch, ooh. So I can change the pitch depending on what I do with my vocal cords, but the pitch doesn't change when the sound travels through walls or drywall or whatever, wood. The pitch stays the same because the pitch depends, again, on the wave frequency, which is determined by the sound source. Okay, let's look a little bit at wave behavior. So waves can be reflected at the boundary between two media. If the reflecting boundary is more dense, the wave orientation will flip. And if the wave is less dense, the wave orientation will keep its original orientation. So let's see if I can find our model for that. Okay, so here is a simulation of a reflection off of a more rigid medium or a more dense medium. You can see how the wave reflects. It actually changes phase or flips sides. This here is a simulation of reflection off of a less rigid or less dense medium, and you can see how the wave reflects off, it bounces off, and it returns on the same side. Okay. Here we have an old video of a ripple tank. A ripple tank is a water-filled tank with a light above it. The light and shadows allow us to see the ripple quite clearly. Here we can see that the angle of the incident wave equals the angle of the reflected wave when a wave hits a barrier at an angle and bounces off the barrier. Here we go again. We've got some wave fronts hitting a barrier, and we can see the shape created. I'll take a screenshot of this and analyze it a little bit further. In the study of waves, we usually don't measure the angles from the barrier. We measure the angles from the normal to the barrier. You may recall that the word normal means perpendicular. So I will be using the markup feature here to draw the perpendicular to the barrier at that point, and then I would mark those angles, the angle between the wave and the barrier. We'll continue with this film and watch a few more iterations of this wave hitting the barrier. So one thing I'd like to clarify is the difference between the direction of motion of the wave and the wave front itself. So the vertical wave here we would call the incident wave. It's the initial wave, and its motion, its direction of motion is perpendicular to the wave front itself. The wave front is the white vertical line. There's our wave front. The reflected wave is down below. It's almost horizontal. And its direction is perpendicular to the wave front. In this final series, we have a series of traveling waves hitting the barrier and creating a pattern. Again, the incident waves we can see are vertical, and the reflected waves are horizontal. The next thing I want to think about a little bit is refraction, and we're going to talk about refraction mostly in relationship to light, but refraction is the bending of light when it enters a different medium. So have you ever wondered why when you look at certain things... Okay, so I'm going to show you a few examples. One of the simplest examples or most common examples is when we have a straw in a glass of water and the straw appears to be cut or appears to not be one straight straw. That's due to refraction, the bending of light. Here's another example. I've got a glass of water in front of a striped background and it looks distorted, the striped background. Here's a kind of a cool picture from Life magazine showing the effects of refraction. This girl's head looks to be detached from her body. Of course, it's not detached. It appears that way because the light bends when it goes through the water. And here's an angle that really shows it nicely. The light actually bends, and it appears to make it look like the pole in this case is bending. So again, the refraction is the bending of light when it enters a different medium. It's caused by slowing down of the waves. And we'll talk about that in an upcoming section. Next, diffraction. Diffraction is the bending of waves around the corners of an obstacle or through an aperture into the region of the geometrical shadow of the obstacle. What the heck does that mean? Okay, if you make a barrier and you send straight wave pulses at the barrier, what will happen is you'll get a curved wave front. The reason for this is that a straight wave front is really the sum of a whole bunch of individual points. And if you create a small opening, essentially what you're doing is just putting one point wave through, and that one point source, it behaves like one point source and it makes a curve. And that bending, that process is called diffraction. So I'm going to show you an example of that. So this is another film of parallel waves being sent, this time at an opening. And here we've changed the wavelength to see how it affects it. But I'd like you to notice how the waves curve at the edges. The waves that are coming through the opening in the barrier are curved at the edges. We'll look at another situation here. That last one looked almost like a point source wave. And then let's take a look. Oh, here's another situation that looks like a point source wave. Again, it's curving. Waves coming through the small opening will curve. And now we're going to increase the size of the opening, and we'll see what happens to the shape of the resulting waves. So you can see the waves fanning out a bit. Now the wave form is straight in the middle and curved on the edges. And this is because of the nature of the source. Oh, here we've got an even wider opening. So I will draw on here. So we want to think of this line wave as the sum of points. Each is like a little point source, but they're all next to each other and they create a straight line wavefront. At the edges, however, we just have a single point, and so at the edge we've got a single point source that creates that curve at the edges, and that's diffraction, that bending or curving of the waveform around due to a barrier. A few more properties of waves. One is the principle of superposition, which says that the amplitudes of two waves may be added together. If the amplitudes are on the same side or have the same, in this case, these are both on the same side, and so we would say they are in phase with each other, we would simply add the amplitudes together. So if, let me pick a better color here, if wave A has an amplitude of 1 and wave B has an amplitude of 1, in the center, when these sum together, they would have an amplitude of 2. And here, if we have the same wave but they're out of phase, wave A is on one side and wave B is on the other side, when they come together, they will completely cancel out. There are lots of simulations of this. So let's go to our O physics and go back to our wave tutorials. So let's look at superposition. And this is something that you can play with. So we'll see when the two waves come together, you can see how they sum together. And I like this one because it shows you the original waves and the sum. Okay, let's see what happens when we make one negative. see if I can hit it right in the middle here. So you can see how when these two waves are overlapping, just for an instant, they will cancel each other out. Actually, if I hit these have exactly the same amplitude, they'll cancel out even more. Let's see if I can hit it just right. I missed it, but right in the middle there, they do cancel each other out. This is a fun thing to play with. Here we'll go in slower motion. There are my two wave pulses. They reflect off of a barrier. Okay, watch what happens right in the middle. There you can see them cancel each other out. Let's see. So for most of this section, we've been talking about mechanical waves. Mechanical waves do require a medium in which to transport energy. Examples of mechanical waves are visible waves like water waves, slinkies, which we'll be playing with in class. And also there are some invisible mechanical waves like sound. Electromagnetic waves like light do not require a medium in which to travel. And one thing we want to make really clear here is that the speed of light is really fast, 3 times 10 to the 8th meters per second. And the speed of sound in air is much slower. It's only about 343 meters per second. I'd like to make sure we clarify some properties of sound waves. They are longitudinal. Remember, that means that they're compression waves. They are mechanical. They require a medium in which to travel. Sound does not travel in a vacuum. It does not travel in outer space. This makes me a not very fun person to go to the movies with, because if there's an explosion during Star Wars and we can hear it, I'll say, oh, you'd never hear it in outer space. Sound waves are three-dimensional. They travel in all directions. The speed of sound depends on the medium, and as the density increases, the speed of the sound increases. So the speed of sound in air is about 343 meters per second. In water, it's almost 5 times that, and in iron, which is a solid, it's faster still. Just a reminder that pitch is indicative of frequency. So high pitch is high frequency, low pitch is low frequency. It's determined by the frequency of the sound wave. And also just another reminder that the frequency stays the same even when the medium changes. I'd like you to have an understanding of resonance. Resonance is what happens when an externally applied force matches the resonating frequency of the object. One example of this from our everyday lives would be a swing. If you've ever gone to a playground and swung on a swing, you'll know that you have to learn to pump at the right time. And that's what you're doing, is you're matching that frequency of the swing, that natural frequency of the swing. So here's one of my favorite videos. This swimming pool is a mass spring system. The pool itself has an elasticity to it, and the water provides a lot of mass. And it has a natural resonating frequency. And what this dad is going to do is find that natural resonating frequency. So he's going to pump up and down at a certain frequency. And you can see he's kind of finding the frequency. And once he finds the frequency, he is able to really increase the amplitude of the wave. And he's increasing it and increasing it. And then he creates a standing wave that is fun for his kids to play on. So once he gets it going, then he invites his sons to try to search that wave. There they go. I thought that looked like a lot of fun. Okay. So that's an example of resonance. The externally applied force vibrations match the natural resonating frequency of the object. And the fundamental frequency is the lowest frequency of vibration that creates a standing wave. Often there are harmonics. There are multiples of the fundamental frequency that will also cause a resonance. But that's a little bit outside the scope of this course. Okay, finally, I want to introduce the concept of polarization. Unpolarized waves travel in more than one plane, and it's possible to have a wave on a string that goes sort of in a circular path or at an angle. If you can imagine having a wave on a string and forcing it to pass through an opening like this, we would say that this wave is vertically polarized. If I were to try to send a horizontal wave through a vertical opening, the wave would disappear altogether. So again, this process of putting a wave into a single plane is called polarization. And we're going to be looking at situations later on in the course where we polarize light waves and see what happens with that.